Hey guys, what's going on? It's Ryan here. Today I wanted to go over a couple quick proofs by induction for exponents and their divisibility. So I'm going to start here. I'm proving that 3 to the 2n minus 1 is divisible by 8 for all integers n is greater than 1. It's written poorly. So I'm going to start with the base case when n is 1. Is this true? So if n is equal to 1, then we're going to have, it's going to be 3 squared, which is 9, minus 1, which is equal to 8, and 8 is obviously divisible by 8, so that works. And I'm going to assume that for all values k greater than 1, that 3 to the 2k minus 1 is divisible by 8. I'm going to write this that it can be expressed in the way 8m, where m is some integer. And the best way to do this is just, it's a lot easier to manipulate it this way. Like, it's hard to express something being divisible by 8 algebraically without using this, you know? Like, obviously it can be expressed as some multiple of 8. So if I'm assuming this to be true, now I need to prove that for k plus 1, I'm just adding 1 to k, is 3 divisible by 8. Now I'm going to start off here. Obviously, I can distribute 2. 2 times k is just 2k, plus 2 minus 1. And so whenever you see stuff like this, it's good to break up the exponents. Obviously, exponent laws, this becomes 3 to the 2k times 3 to the 2 minus 1, or 9 times 3 to the 2k minus 1. Very good. Now, I don't know if you guys see what I see, but I'm seeing here that 3 to the 2k minus 1 is divisible by 8. And right now we have, is 9 of 3 to the 2k minus 1 divisible by 8. If I'm assuming this to be divisible by 8, I want to create that somewhere in this equation, you know, to start it off, like to show that that section is divisible by 8. Now, obviously I don't have this directly in here, but if I have 9 of 3 to the 2k, I have 9 of these, right? I can split it apart. This is the same as 8 times 3 to the 2k plus 3 to the 2k. That creates the 9, 3 to the 2k's minus 1. And this right here, we said is already divisible by 8. And so if you have like a plus b, and you're trying to figure out if it's divisible by c, if a is divisible by c and b is divisible by c, then a plus b is divisible by c. Right now, this is our a and this is our b. We know that 3 to the 2k minus 1 is divisible by 8 because that's what we assumed. So this works, that's divisible by 8. Now we have to figure, is 8 times 3 to the 2k divisible by 8? And obviously, yeah. I mean, if you divide this by 8, it's just going to give you 3 to the 2k, which is always whole number. So this is true. So we have proved that for k plus 1, 3 to the 2k plus 1 minus 1 is always divisible by 8. And because we've proved this to be true, then we know that for all values n greater than or equal to 1, 3 to the 2n minus 1 is divisible by 8. And if you don't get like why that works for induction, like why proving that makes sense, it's because we figured out that it's true at 1. And so if it's true at 1, it would satisfy this, right? But what we prove when we do k plus 1 is that if it works for k, it works for a value 1 greater than k. So if k is equal to 1, which we've plugged in and worked out that it is, then k plus 1 will also be true, which is just 2. And so if it's true for 1, it's true for 2. You add 1, it's true for 3. You add 1, it's true for 4. And that just goes on for infinity. So that's how the induction works. And so we have proved this. And so I have one more. It's a little bit more complicated. Prove 2 to the n plus 2 plus 3 to the 2n plus 1 divisible by 7. And so I'm going to start off for n greater than or equal to 1. I'm going to start off like the last one. Test, is it true for n equals 1? Which for this becomes 2 cubed plus 3 to the 4. 3 cubed, geez. Mental math is awful. Which becomes 8 plus 27, which becomes 35, and 35 divided by 7 is just 5. So we know what works for n equals 1. Now, we're going to assume for k that 2 to the k plus 2 plus 3 to the 2k plus 1 is divisible by 7, or it's a multiple of 7, so it can be written in the form 7m. So now we have to think, is it true for k plus 1? And so I'm going to write it out. If I'm doing k plus 1, it's just going to be 2 to the, if we have k plus 2 and we're replacing it with k plus, if we're replacing the k with k plus 1, this is just going to be k plus 3. And 2 times k plus 1 plus 1. Further simplifying, this just becomes 2 to the k plus 3 plus 3 to the 2k. 2 times 1 is 2, plus 1 is 3. Okay, I think the way I want to go at this right now is I want to rearrange this equation right here. We have a base 2 and a base 3. I don't like that. If I can get it all as one base, I can maybe better simplify it. So I am going to say that 2 to the k plus 2 is equal to 7m minus 3 to the 2k plus 1. And this is good because we have 2 to the k plus 3 here, which is just 2 times 2 to the k plus 2, right? And so I'm going to replace this right here with this. And so this whole expression right here becomes 2 times 7m minus 3 to the 2k plus 1 plus 3 to the 2k plus 3. I'm going to distribute the 2n. It's 14m minus 2 times 3 to the 2k plus 1 plus 3 to the 2k plus 3. Now I want to break apart these exponents here. Yeah, that's what I'm going to do. If I have 3 to the 2k plus 1, that's the same as 3 to the 2k times 3. And then the 3 times the 2 is 6. So it's going to be 14m minus 6 times 3 to the 2k. If I have 3 to the 2k plus 3, that's the same as 3 to the 2k times 3 cubed, which is just 27. So I'm going to be adding, 27 times 3 to the 2k. Lastly, I have a 27 3 to the 2k, and I have a negative 6 3 to the 2k. And so 27 minus 6 is 21. So this is the same as 14m plus 21 times 3 to the 2k. Now it's like I did in the first example. Is this divisible by 7? Well, if both terms are divisible by 7, then the whole thing is divisible by 7. 14m divided by 7 is just 2m. And 21 3 to the 2k divided by 7 is just 3 times 3 to the 2k. So because this is divisible by 7, then that means that when I do k plus 1, it holds true, it's still divisible by 7. So because that works, then I have proved that for all values n greater than or equal to 1, that's an integer, that 2 to the m plus 2 plus 3 to the 2m plus 1 is divisible by 7. And so that just shows how neat induction is, just like how simple it makes things. Like without induction, I don't even know where I'd start for a proof like that, but induction just simplifies it so much. You just work through it, you apply the assumptions that you make, and it all works out in the end.